about it, right? What to do, what's expected, how can I get this done in 5 minutes, right? 5 minutes demonstration. Again, I would like for everyone to bring along a laptop, and we can do the demonstrations in this room. If someone else should be coming into this room for cleaning purposes or whatever, we can just go to the lobby area here in this building and continue demonstrating there. Again, the first project requires you to implement a raycaster using trilinear and tricubic interpolation, so the generation of pictures, particularly the tricubic-based pictures, takes a lot of time. So therefore, you have to have a bunch of pictures already generated on your system that you just bring up. Okay, you have to show me, Bernd, these are the resulting pictures when I use the following parameter setting. This is based on this color model, on this transfer function, and this is based on this sampling resolution. This is a resolution for the mesh, for the screen, and for the samples along the way. Blah blah blah. You have to give me a bunch of pictures. Okay, show me that. But besides that, I also would like to see how you actually run the program. Right, so we should start with looking at pictures that you have generated based on different parameter settings. Right, so he impressed me right away with great results, boom, 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 and that goes quickly. And then toward the end of the demo, I would like to see how you actually execute your program. Okay, show me your interface. What are the parameters that you have to type in, that you change with the dial, slider, button, whatever. So I see what the different parameters are that your program supports for the user to play with. Okay, but again, we cannot sit there and wait 5 minutes for the first picture to build up line by line. That takes too long. All right, and again, it's better for you to demonstrate a project, even if it's not completely done, even if it's not completely bug-free. Because if you keep on working on it, you can work on it forever, right? The ultimate raycaster will take forever. It's never done. So it's better to demonstrate something early so you can begin working on the second project, third project, and your own project. This Thursday night, I will bring up a little sign-up sheet, and everyone can pick a time, okay? And then if some want to demonstrate Thursday night instead of Tuesday night, we can do that too. If some want to demonstrate 1 week later, of course, I'm fine with that too, but you shouldn't be fine with that yourselves, okay? So we'll see. And if you have not started with the first homework assignment, at this point, start right after class, okay? It is really not that easy. It might be easy conceptually, but actually getting it to work, it's a different thing, right? You know that. All right, and so I know that there are some questions about the first project, so anyone shoot at me, and I will try to answer your questions as best as I can for everyone. Jennifer.
So in the last lecture, when you were explaining how you get the alpha values and the color values, you said for the color it's just the inherent color of the material, but how would we know what the inherent color of the material is for, like, say we just make a spherical shells? Do you just make up a color or something?
You make up a color. Okay. The easiest way to see whether the basics of your raycaster work is to work on a medical data set. On a simple CAT scan, computerized axial tomography or computer axial tomography data set, CAT scan. Why? Because the resulting pictures should look like an X-ray. Okay, they should look like a grayscale picture. So that's a good one to start with. So you don't worry about color properties. Okay, it's just gray. So different shades of white, from 000 to 255, 255, 255, and gray levels in between. Then you don't have to worry about the real color, just intensity essentially. If you want to worry about realistic color models, there are actually lookup tables out there. There are lookup tables out there that define what are the inherent color properties of different materials when they are illuminated by certain light sources. Okay, and so you can look them up. If you want to go beyond the first assignment and get some additional credit, well, look up what the color properties of an amethyst are. And if you want to do that, maybe you find a good resource where if certain wavelengths are coming in, RGB, then certain wavelengths are being absorbed by that thing and certain wavelengths are coming out of it again, right? Yes, one would have to do that in general, to have a realistic raycaster. Do I know the answer to that? No, I would have to go to lookup tables myself to textbooks out there, where probably for different materials are there measured, observed, experimentally observed color behaviors described. Otherwise, you play with the transfer function and you make it up. And you also play with this K sub D, the diffuse color property for the object itself that you illuminate. Okay. Make it look gold, make it look silver, make it look whatever colors you like. Ultimately, the structure has to show, right? If there's a structure of concentric shells, well, the picture has to show concentric shells. If you illuminate or raycast a skull data set, well, the structure of a skull has to show, right? The teeth have to show up, the gold has to show up, and so forth. Does it help? A little bit, okay. Shoot.
For the first project, we're asked to support to deal with the rectilinear data set, but I can only find regular grid data set on the website. So can we find the rectilinear data set somewhere else?
I don't want you to worry about anything besides Cartesian grids. I think I went over that too quickly last time. I want you to use the simplest data set there is, a grid that is essentially based on the index of the data samples itself. Okay? Only use Cartesian grids. And in fact, you don't even store the coordinates of the grid corners, okay, because they're inherent. So these are integer grids where the coordinates of these corner points are the indices, right? So if this is x, then the x value of these lines are indeed integers. Okay, so they would go from 0 to maybe 63, right? And this would be your y coordinate. And again, the location of these grid cell corners would be between 0 and say 63. So you have a resolution 64 squared data set, right? With 63 squared cells in it. And this is a rectilinear data set. It's rectilinear because there are right angles everywhere. It's the rect in there. And then it's linear because the connection from point to point in the cell is linear, it's a line. That's why it's called rectilinear. Okay? And it's called Cartesian. It's called Cartesian because the x-coordinate of the grid points themselves are integers, are the index. So you don't have to store anything. You really just have to store the function values, right? This is function value f00, and this is function value f63, 63. That's all you need, a two-dimensional array. And the index of the array is automatically the coordinate of the corners. Makes it simple, okay? If you want to get additional credit, I think I mentioned this on the additional credit. Even if I don't mention it, you could do that. If you want to get additional credit, you can show me that you can visualize a data set like this, where the spacing is maybe changing in a geometric way. But then you have all kinds of issues because there is not a uniform spacing. The spacing is different. No longer are these distances 1, and everything changes, okay? All the formulas change. All the gradient computations change. Gradient estimation changes. The Bezier apparatus changes everything, okay? So, but if you can convince me that you handle it properly, fantastic. And then if you can also show me that you can do this, even better. Okay. This is Cartesian. It's a rectilinear mesh. This is a rectilinear mesh, which is no longer Cartesian, but it's still rect, right? Right angles everywhere and lines. This is still curvilinear. It's called curvilinear, curve in there, because we are giving up the right angle condition at the grid cell corners, but it's still curvilinear because the connections from point to point are lines. Okay, that's why it's called curvilinear. But there is an illusion of a curve there, right? So curvilinear. And then if you want to give that up and want to become more general, you also can show me that you can handle these types of grids, where the elements no longer are even linear, but they are really curved grid elements, where the edges are no longer lines, but the edges themselves are already curves. It becomes more and more complicated, okay? to do proper rake, you can assume that this is probably quite difficult to do that, right? You need all kinds of inside-outside tests and intersection tests. When I'm in cell A, when am I in cell B? In the real world, you have to deal with that. Okay. Only this. Very simple stuff. And also for the pictures that I want you to generate, again, the most simple pictures. You take this Cartesian mesh, and this is your image plane, okay? One image plane is parallel to the y-axis, and the other image plane is parallel to the x-axis. And then you have to decide a resolution. The user is sitting here, right, the viewer, and you have to decide a resolution for the screen. Okay? And you also have to think a little bit about resolution and parameters, okay? What are the 3 most important resolutions or sampling that you have to worry about? Well, here is the resolution of the mesh, 64 by 64 points. Okay, that's one resolution. And I ask you to do that. I want you to use a relatively low resolution data set, 64 cubed, say, in 3D. That's good enough because I want you to see the difference between trilinear and tricubic. If you use a super high resolution data set to begin with, you will not see a difference in the limit. And I also don't want you to have to wait forever to get an aha experience. Okay, I want you to get an image quickly. So relatively low resolution here for your data set. For initial program development and debugging and all of that, you wouldn't want to even have a smaller one. And then you have to worry about the resolution for the screen for your little drawing window where you shoot the rays through. And that resolution probably should be higher than that. Why? Because you would like to have multiple rays going through the cells, right? So if I have this resolution here, you have multiple rays going through there. Okay? So you would like to have this resolution maybe 3 times, 4 times, 5 times as large as the resolution here. So maybe this here is a resolution from 0 to 255, right? Pixels. And then the other resolution you have to worry about is the resolution for the rays, right? You also have to determine how many samples you want to have on each ray. And rule of thumb for your first assignment, try to use between 4 and 8, okay? Between 4 and 8 sample points along a ray inside each cell. Okay? And if you want to experiment a little bit, then you can vary all this resolution and see how the pictures change, right? It is very cool to understand the relationship between these different resolutions. There is a relationship. The other issue is all the theory I described was just for one particular cell. Right? And I said every cell can be treated as if it was a unit cube, parameterized from 0 to 1, from 0 to 1, from 0 to 1 in the 3 directions. How do you get the x, y, and z coordinates for a sample point inside a cell? Well, you get it by subtracting the index or the indices of the lower left front corner. Right? So if you are in a particular cell, this particular situation, and you have this one cell, and this cell might be this might be location 11, and this is location 12, and here in y, this is x. This might be 12, and this might be 13. Then somewhere you have a sample point, right? What are the local coordinates of this point relative to this cell if I want this cell to be parameterized between 0, 1, 0, 1? How do I get a number for this guy that is between 0 and 1? Locally, I want to parameterize this thing using coordinates varying between 0 and 1. So the sample point in the mesh has a coordinate. The way I have drawn it, it looks like 11.4, right, and maybe 12.3. So what are its normal, it's parameters relative to the cell itself. Come on, trust your intuition. Huh? Pardon? 0.4, 0.3, you just subtract the coordinates for the lower left corner, right? So this becomes locally 0.4 and 0.3, right? And these are the numbers or the parameters that you have to use for the whole Bézier machinery, the Bézier polynomials, the evaluation, and so forth, right? Okay, so you just subtract the integers in front of it. All right. You also had a question, right, at the beginning of class. You only asked me, but you really now ask in class, so everyone gets the answer, right? So, shoot. Can you ask in the microphone?
Say again?
No, I mean ask the question again, and I will try to answer it. But speak in the mic.
You mean the question that I asked?
Yes, yes, yes.
Oh. I think you already answered it, Professor. The question about its I just asked you what does the cell means at that time. Yeah.
Does this clarify the relationship
you clarify,
between the mesh, the screen, the sampling along the ray, and the local coordinate system for a cell within the context of the entire mesh? That relationship is clear, right? Mm-hmm. You didn't have another question about the lighting model? Didn't you have a question about the lighting model? Inside a cell, I thought so. This is just one cell. I have a ray, a happy ray going through there. There's a sample. Mm-hmm. And then, did you have a question about the color? How to get the color?
Yeah.
How do we get the color for a sample point? Someone help me. Shoot.
So you can use the Phong lighting model.
The Phong lighting model.
And so what you have to get the gradient, which will then act as your normal in the Phong lighting calculation. And you have to specify where some light source is. And you also need to compute a reflection vector based on the viewing ray. And then you need to know what the inherent color of the material is, and then you should be able to plug all of that into the Phong lighting calculation.
These are the parameters you talked about, right? Essentially. So you said there's a point. We do this magic gradient computation. The gradient gets normalized, right? Becomes a normal. Then there's a light source somewhere in three-dimensional space. And then this becomes in the Phong model the light vector. Then lighting, there's a reflection vector, and there are formulas how you get R from L, right? You remember that? And then there is the view vector. The view vector is just from the point to the eye. If the viewer is infinitely far away, then that's just always the direction of one of these coordinate axes, right? Negative. Yeah. So Phong model is intensity or color at that point is ambient color property plus diffuse color property plus specular color property, right? And again, how to do the Phong model and what the parameters for the Phong model are, you can use any standard Introduction to Computer Graphics book to do that. And these books differ, okay? I mean, I gave you one formula, but all the books have a slightly different take on that. So pick one. Okay. Are you really clear on everything? Okay. This is the last time, really, that you can ask me questions, because on Thursday night you should be fully up to speed already on your implementation. Shoot.
Does it matter if we use perspective projection or
yes,
orthogonal?
Big time. Why does it matter? He's asking perspective projection. My viewer is infinitely far away, right?
Yeah.
What does it allow me to do? All my rays are follow your thoughts, more intuition. What do I want to say? All these rays are parallel. Why? Because my viewer is infinitely far away on the x-axis, or is infinitely far away on the y-axis. If I do this in a perspective projection way, yes, it gets more complicated. If you want to do that for your project, you can do that. You get additional credit for that, by all means, yes. But what happens when I have perspective projection? Well, if that is the mesh, and your viewer is very close to the mesh, or maybe even sitting inside the mesh, so viewer is here, and this is viewing direction, okay? And you have a perspective setup. Perspective setup means you have an opening angle, right? The viewing, it's called the viewing angle, right? That's focus length of your lens. Then all the rays would be these rays. All the sampling, all the computations would be much more complicated, right? Because you have this fan of lines which originate from a point rather than having a family of parallel lines. It doesn't become too much more complicated, but it gets a little bit more complicated, okay? Why? Why is it more difficult? Because all these lines are very close to each other, relatively speaking, close to the eye. The deeper you go into the volume, these rays open up and they move further and further apart from each other, right? In this parallel world, even the cells deep in the volume have an influence on the resulting picture, right? Because if these are 5 rays here, 5 entering, there are still 5 rays here, because they are parallel. As soon as you go to a perspective model, whoop, what happens? Well, here is a bunch of rays here entering there, but here the density of rays hitting the cells goes down. So that has an effect, and you want to somehow deal with that. The other generalization is, these are just ideas if you want to do that. So you still use a Cartesian mesh, but no longer will you just project onto these coordinate system planes, this plane or that plane, right? By doing this, you get simple pictures. Now you have an arbitrary orientation for the plane that you project onto or that you raycast onto. So a more general setting is you have an arbitrary viewing plane, and its resolution in pixels here, and the viewer is happily standing here, but still at infinity, far away. So you have a bunch of parallel rays like this. Okay, again, this is more general than that. You see that right away, right? But a real system has to support that. Why? Because the user, of course, wants to fly around the data set and look at the data set from any viewpoint, right? Not just these. But again, for the first assignment, I want to make it simple. Did this help?
If I do perspective projection...
Did it help a little bit?
Yes.
Okay, good.
If I do perspective projection, do I still have to guarantee the same number of samples per voxel? Because the rays sort of pass at different angles and...
That's a good question. You're a scientist, right?
No, kind of. Hoping to get there.
Yeah. So if you have this perspective thing, all these rays, this is the ray bundle, right, that's going in there. Right? The further these rays are away from the eye point, the more they open up and the bigger is the distance between. So the question is, I guess, whether at some point you want to have additional rays inserted at some point, right? And also contributing in some magic way to the final image. Does it make sense? Yes or no? Do you need that? Yes, you need that. Of course. Of course. Why? Because all these points here, all these there's a volume here, right? This is the material. All these material pieces, of course, they have radiative characteristics. They are contributing to the overall color property that my eye living here sees. So yes, you want to make sure that this entire volume, viewed as a continuum, has an effect on this integration part. The trick is, when you go from a sampling of, say, 4 rays to a sampling of 8 rays to a sampling of 16, yes, you have to increase the density of these things to be physically accurate. But then you also have to worry about the proper weights. How to combine them. Here, four rays. How do you combine the individual contributions? Then you have more rays. How to combine? You need some kind of notion of weight, right? How to combine it? How to average it? This is a good research project. You have to go into the physics ultimately to really do it well. But again, many of these types of problems are forgotten because you just assume that the viewer is very far away from the actual object. And as soon as you are in a setting where the viewer is far away from the bounding box, then you don't have these problems. But yes, if you have a candle and you have a burning candle right in front of your face, right, and you're in front of the candle and you want to, right, raycast the candle, then these effects have to be considered. Okay. Any more questions about first project? No? Again, first project have a bunch of cool pictures generated based on the trilinear approximation, based on the tricubic interpolation, and use different parameter settings, right? Resolution for the screen, resolution for the samples along the ray, different data set, concentric shells, a skull data set, maybe a flame burning, combustion data set, whatever. Pick a few. And start with data sets when you debug your program that you understand. Start with very simple functions like the concentric shells, right? If you know my data set represents a concentric shell-like feature, then I should see that, right? If it doesn't show that, then there's something inherently wrong. And that's what I have to see. I first want to see the simple structure, so I'm somewhat convinced that your implementation might be correct, and then you go to more complicated stuff, right? Okay. Now, for final, potential additional credit, I also talk about using these higher degree approximations to support the other basic visualization techniques. And the other basic visualization techniques are, what is this for? Slicing, right? You already have this tricubic representation. So if you wanted to show me a tricubic visualization of this scalar field, you can also have a slicing plane, right? This is the plane that you move through there, left to right, additional credit, relatively cheap additional credit. And the slicing plane, when you compute the samples on this guy to grow shade it, then you just again evaluate for these samples on the plane inside a cell. And there will be a difference regarding, for example, cutting through this onion, these concentric shells. For the trilinear one, the spherical patterns or the circular patterns you will see in the slicing plane will be less circular in the trilinear and will be more circular in the tricubic. Should be. The other thing is contouring, right? For example, again, if you have a very simple function, test function, f of x plus z equals x squared plus y squared plus z squared, where the contours are, well, mathematically perfect spheres, then, well, with the trilinear approximation, you get something like a sphere or a good tessellation of the sphere. With the tricubic, you get a tessellation that is better an approximation of the sphere, okay? So whatever, if you want to go in this direction, this would be relatively cheap additional credit, the slicer, right? And again, I'm happy if you give me a slicer that is parallel to the coordinate system plane. It doesn't even have to be an arbitrary slicer, okay? Now, this is a challenge. If you want to do this for your final project, you can use your first project as a basis for that, and then really push it in the direction of parallelization, GPU programming, and shader programming, and real-time raycasting. What would I like to see? This is an idea. I don't think you can do this for the first project as additional credit, but you could do this for the final project if you want to go into GPU programming. For example, this is my domain, and say I have a skull data set. So that is person happy. But in order to really get an understanding of the 3D structure of every bone, every muscle, every gold plum in there, how do I get that? I really have to rotate the thing around, right? Not only that, I would like to use a flashlight. I would like to have a light source that I can place, not just one light source, multiple light sources that I can place inside that data set, inside the skull, right next to the skull. I would like to have a real-time program where you have flashlights placed anywhere. And on top of that, I can also rotate this thing. Okay, see that? I really get a much better understanding if I'm, say, planning a surgical intervention to prepare surgery. I really have to understand intuitively what the structure is like before I make cuts. So again, a three-dimensional data set, skull data set, grayscale is good enough. This is about the real-time aspect of things. This would not be about beautiful, pretty color images. This would be about the speed. Again, grayscale CAT scan data set and multiple flashlights, light sources that I can interactively place and move around in real time. I can in real time move the location of these multiple light sources. And whenever I move a single light source just by 1 millimeter or by 1 grid cell, then the new raycast image should be there in 1/24th of a second. Right? That's what I want. At the same time, not only want I be able to move the light source around with my hand, but at the same time I also want to be able to move around with my viewpoint, right? So you have to synchronize that. So the bottom line is you need about 24 frames per second for the left eye, and if you do it in stereo, 24 frames for the right eye. That's the challenge, right? Do this type of thing. As a viewer, I go around this data set, and also I use my hand to change the position of the light sources. And this data set is 512 cubed, at least. Okay? And I want to get a picture that is of resolution 1024 by 1024. I want to get real-time response. Okay? So I want to do this for a 512 cube data set, and I want to do it for a screen that has 1024 resolution. And I want to do the rendering at about 25 frames per second. Okay? You can do that. It's great. And as you already know, many of these steps that you have to do for raycasting are inherently parallelizable, right? There's no real difficulty there, but you have to do it. All right, cool. That's enough about the first project and ideas for a final project based on it. Take a look at this. You have to tell me which diamond is the real one, and which one is simulated, and which one is a photograph. Okay, this was our goal to achieve this on a Sony Vaio laptop about 8 years ago, and we achieved it. Okay, this is based on the real physics of a diamond, and we took photographs from a jewelry store, and under specific lighting, measured lighting conditions, and then we wrote a ray tracer that also has elements of a raycaster for this diamond, and the diamond is very pretty. I still have it in my office. Okay, the computer-generated one is nearly as pretty as the real one. So take a look. Okay. So the next topic is vector field visualization. Vector field is notation so in the context of visualization, typically what we are given is a bunch of vectors that are associated or measured or affixed to certain points, and so they live somewhere in xy space, and each of these data would consist of a location xy and a vector component uv. So a 2D steady field would be a vector field v. Sometimes I will make this arrow on top of the v, sometimes I won't, because it is implicit anyway. And the components will usually be written as uv. And the UV, the direction, the vector, and its length really depend on the location. So these are two coordinate functions. U depends on the location xy, and v depends on the location of xy, but nothing else. Now, if you have something that is called 2D steady, then there's also something that is 2D unsteady. Or time dependent. That means that the vector field would simply change over time. Say, I have a little cell, why not? A little hexahedral cell, quadrilateral cell, and this is for time 0. Then for time 1, at the same cell corners, I might all of a sudden have different behavior, right? So at the same locations, I have a different vector field behavior. So, and here is my running time. And so I would write such a field as a vector field depending on x and t. X, or point x, boldface notation, is the location, and t is the time variable. So here, the two components depend on both xy and time. On xy, the location and time. If I can play this game in 2D, I can also play it in 3D. So I have 3D steady vector fields, in which case they would simply live in xyz space. Nothing special, so I have a point with a fixed vector, and I would call the vector a function of x, y, and z with now 3 components, u, v, w, depending on x, y, z, or depending on x, y, z, and the third one as well. If I have 3D steady fields, I also can have 3D unsteady fields, and that's as difficult as we will get in this class. 3D unsteady and again, you can imagine the flow in this room, right? We have air conditioning, and the flow field is always changing as a function of space and time. So we have a vector field, which is a vector field depending on x, y, z, and time, which is u, v, w based on x, y, z, and time. You have all of this in your notes or in your textbooks from the introduction to flow visualization. Now, there also were some very basic methods that we learned, right? How to make pictures of these flow fields or velocity fields or vector fields. Tell me again what these basic methods were to make a picture of a flow field. Anyone? Anyone who has taken Introduction to Visualization 177 knows many methods to make a picture of a flow field. Streamlines. Anything else? Who gives me more than streamlines? Streamlines? Pardon? LRC, Lick. Okay, that is much further advanced. LRC is cool, I like it, yeah, but it's built on streamlines and much more. So streamlines and more simple things. Streamlines. Be brave. Scream. Holler. Shout. Whatever. Streamlines. There is something that is called something very similar.
Pathlines.
Pathlines. Streamlines, pathlines, what else? Streaklines? Timelines? Trajectories? What are these things? Why do we have to worry about all of them? Do you know the difference between them? what are the differences? The differences are in the math books, right? In the math books are formal definitions for streamlines, streaklines, pathlines, and timelines. As computer scientists, at least we have to have an intuitive understanding of what it means qualitatively to produce pictures of those four. Okay? Let me try very intuitively, and I will not put this on the board because it's in the books. Okay. Let's start with the simplest one. The simplest one is called, these are the basic Viz methods. Basic Viz methods. Viz methods. The most basic one is a trajectory or path line. Okay? Trajectory, or, this is the same thing, it's just a different word for the same thing, or path line. Okay? And you can put into your notes what I describe in words now. What is a trajectory? Anyone help me? What is a trajectory or a path line? Flow field, the flow in this room. I will release a little helium-filled balloon in this room, and this helium balloon will do what? It will be happily tracing out a path. Okay, that is the path line of that thing, in a sense. Actually, there is also mass and gravitational forces involved, which we all forget in our visualization things. But forget about that. So again, the trajectory or the path line is the curve in space that is traced out over time by a particle in that field. Okay? Huh? Again, a path line or a trajectory is a trajectory of Starship Enterprise that it's taking when it's just floating in space without any kind of forces acting on it, except a field itself. Okay? Path line, so the flow. The particle, a massless particle, is just in the flow, and it will be moving with the flow without gravitation acting on it. The particle will be moving with the flow in the direction of flow at any location at any point in time. That is the trajectory or the path of that particle. Okay? All right. This is the same. 2 is, let's say, streaklines. A streakline. What is that? A streakline. 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 What is the meaning of a streakline? Streak. All these words and these methods come from experimental fluid dynamics, where people actually had water tanks and did experiments with understanding water flow. So one experiment that they do is there's a water tank underneath you, okay, and the water is flowing in certain ways, but the water is transparent. I do not see how the water is flowing, so I want to see it. So what do I do in order to see how the water is flowing? I just have a little pot of blue ink colored water. I pour it into the water underneath me, and I will see where the blue ink is flowing. That's called a streak. It's inherently different from a path line. See that? It's very different. The path line was just the curve traced out by one particle. It is, if I release this piece of chalk, which has no mass, in this airflow in this room, then it will be moving something like that. And this curve is the path of this piece of chalk. Now, again, the streak is different. There's a water tank underneath me, and the water is flowing. And here I have a little pot of colored ink, and I just release this water in a continual fashion into this flowing water. And then, well, this blue thing, there will be this blue streak in there. And this curve is a streak. But again, you have to remember that these different blue dots that are in there have different ages, right? Because, I mean, the stuff that leaves my pot here, my cup, first is the oldest ink that is already there, right? And then there's new ink being poured into the water. So it's different, right? So that's a streak, however you phrase that in your book, but that's where it comes from. You release colored ink into a water tank, right? And the streak shown by that ink is a streak line. That's what a streak line is. The other issue is a timeline. No, it's a streamline. Next. A streamline. What is a streamline? The vectors are given to us. These are curves. These are all curves that are constructed based on the vector field. Okay, for the first ones I described, time played a role, right? Time was playing a role. When I had this piece of chalk and it was flowing around here, well, then I also assume that the air conditioning and the wind in this room is changing, okay? This little starship here is exposed to a changing wind field, okay? All right, so time changes. When I have this little cup of blue ink and I pour it into the water tank, again, time. This is a time phenomenon. I will have this water hit the water tank at different time points, second 0, second 1, second 2, and so forth. And the water underneath me, the water tank is also changing over time, right? Now with the streamline, I keep time fixed. Everything is fixed with a streamline. With the streamline, I just take a snapshot, a photo of the wind field in this room, the air, right? There is no, I just measure for this particular time, 7 p.m., the velocity vector at every point in this room. That's it. And then I stand still. And then I analyze just that photograph, that moment of the wind field in this room. Okay? And then you compute what is called integral curves or tangent curves for that particular instantaneous flow field. Okay? Streamlines are instantaneous tangent curves for of a vector field at a specific moment in time, of a vector field for a specific time, for a fixed time. Okay. And the last one is called, well, you didn't, maybe you have not heard about this guy, a timeline. Who has come across this one, the timeline? Have you heard of timelines before? Okay, again, you have to understand it intuitively and qualitatively what this means. The timeline, okay? I have a pipe here, and there's water flowing through this pipe, and there are little holes. This pipe, like a flute, okay? And then through these holes, water is dropping down. Drops, they are synchronized, okay? So I have, say, this pipe has 10 holes, and there are 10 drops falling down out of this pipe at the same moment in time, at 0 seconds, 1 second, 2 seconds, 3 seconds, and so forth. And they are hitting my water tank. Okay? So all these drops have the same age. They originate at the same moment in time. Okay? So there's this creek, this river, the water tank underneath me, and I have 10 water faucets. 10 faucets, and these 10 water faucets, I all open them, and I synchronize them in such a way that whenever these faucets have a drop come out of them, the drops are falling down at the same time points. 10 water faucets are all on a line. That's the line. And they are synchronized in the sense that they have drops coming out of them at the same time. So I could connect these drops right in a line fashion, drop number 1 with drop number 2, drop number 3, drop number 10 for 0 seconds, and then these drops will all hit the water tank. Call them blue. Okay, these are blue drops. And then these blue drops, they look like a curve if they are dense enough, right? And then this timeline will evolve in that water tank. And then at second 2, there will be another family of drops all falling down at the same time point. And again, they will look as if they were stretched out in a line. and then they will move forward with the water. So that's the timeline. So they show the fate of a line over time when exposed to the water tank. Again, you can formalize all of this mathematically, but we won't do this here. If you get the concept and you really are very clear about the distinction between these four essential things, then I'm happy, okay? But I really want you to understand that these four things are very, very different. They produce very different pictures, okay? Very different pictures. All right. That's that. The most important one that was mentioned also first by you is a streamline. Why? Because it allows us to analyze a field for a particular fixed time. That makes things simpler. Okay? That's why most visualization methods are based on the streamline, the line that results from analyzing a field for a fixed moment in time. And by the way, I should tell you that, remark, for a steady field, for steady fields, 1, 2, and 3 are the same. 1, 2, 3 are the same. But for unsteady fields, 1, 2, and 3 are all mutually different. For unsteady fields, 1, 2, 3 are different. What are the types of pictures? Types of pictures. The types of pictures that you want to generate. The types of pictures that you want to generate look like this. I am in the plane, in the xy plane. I have a little spherical obstacle. I do a simulation in the neighborhood of this obstacle, and I get a bunch of points with associated vectors. And if the wind is blowing from this direction, okay, then the streamlines I will get will probably look like this. Okay. Those are the type. That is a type of picture we would like to see when we are given data like this, points with vectors, right? This is our input, the happy little points with simulated or computed or experimentally observed happy vectors, and we want to compute these streamlines. So time is fixed, and these guys are streamlines computed from given points with associated flow vectors, or velocity vectors, given points and velocity vectors. Now I want to motivate something right away. When you are standing far away from this phenomenon and the wind is not blowing that heftily, then this picture is cool. But what will probably happen if the wind is blowing at increasing strength and if you were to zoom in? Then this phenomenon gets much more complicated, okay? But, and this leads to another topic, but it can get much more complicated, much more complex when velocity is high, velocities are high. Okay, then you also want to zoom in. Okay, and then the situation looks completely different. So all of what you have here, you have a bunch of parallel lines, parallel curves. In a sense, they are parallel, right? More or less all parallel. No. So, but if the speed increases and the you zoom in, you will see the following phenomenon. I will try to sketch something that is hopefully close to being realistic. Certain lines will behave like this. I zoom into the area right behind that circular object, right? And this goes on and on and on. Well, not really. If you're really far away, when you're far away, then you still have this behavior, right? But so this is called a vortex street or a vortex streak, that behind the obstacle you have these vortices or eddies or critical points that are of focal nature. But this is not all of it. You can zoom in there. When you zoom in and you do a simulation that is at much finer scale, you will also see this. Okay. The structure becomes more and more intricate the finer and finer you resolve it. Okay, but this is not it. You can zoom in and focus on that one. What will you see? Okay. This is the phenomenon of turbulence and vortex streaks. It's not understood. So, complex vortex behavior. What might these vortices be in the case of a three-dimensional flow? What are they in the real world? In the 3D world, the world is really 3D. What are these things? The spinning stuff. What is this dangerous spinning stuff? Tornadoes, hurricanes, typhoons, swirling water masses that swallow ships, etc., right? So these are tornadoes in 3D. And so the interesting thing is these are critical points where the speed is 0. Okay. And in this case, these are focal points. So this requires us to understand topological methods. These methods to just make a pretty picture doesn't suffice anymore. You want to understand the structure, but in order to characterize a structure of something like this, you need topology, okay? So that's where we need topology methods later. We need topological analysis, topological vector field analysis. Okay. How did you compute these streamlines? Who already generated streamlines? At least half of you. Right? You generated a streamline before. You generated streamlines before. You generated streamlines before. Come on, that can't be. Who generated streamlines? You did. Okay, how do you do that? The streamline is a line. In computer graphics, we represent a line or make a picture of a line by using polylines, polygons, a bunch of points connected by segments, right? So how do you get the points of the polyline for the streamline? That's what you have to do, right? compute the streamline by generating a bunch of hopefully good points on it and then connecting them with little line segments in between. And we say that's a streamline. Well, it's not really, but we call it that anyway. So how do you get the points on this polyline thing? How do you get the first point? Can you sample things? Well, you have sample points with associated arrows. How do you get a streamline in this room? The first thing is you decide on where you place your initial point.
Right.
And then, at this point, you have a flow field, a velocity vector.
Can we think of it as a Laplace equation, or is that not applicable?
You only are allowed to use the data that you have. You just have this initial location and the vector.
dx, dy, dz.
You just follow it.
Three-dimension.
You just follow this point in the direction dictated by the vector that you know there. The question is, how long can it stay on that arrow, on that line that is dictated by the arrow, by that vector? Not for too long, because the field is changing, right? Things are spinning around in this room. Come on, you guys have done this, right? Who is a streamline expert here in this room? Sure.
Can we just do dx, dy, dz with boundary conditions?
This is much simpler. This is much simpler. If you're on the right, this is an initial boundary. It's an initial condition for a differential equation. Yes, of course. But let's follow that. Okay, streamline approximation. We don't get the real ones because we cannot. Streamline approximation. The most primitive one, method 0, is just called the Euler method. Euler method. Have you seen the collected works of Leonhard Euler? Do you know how many books he wrote in his lifetime? He wrote many books. Look it up. Okay. How many books did Euler write in his lifetime? The number is astonishing. Not papers, these are books. Okay. So we have a point and we have a vector. This is an xy. This is an initial point, and for point I just will use boldface notation, x0. And we want to know, well, where's the streamline thing here, right? So this might be the real streamline, which we don't know. We want to get it. We only have this. The simplest way is to just take this point and follow in this direction, dictated by the arrow that we know there. So you just say, okay, I just stay on this direction, and I call this point number 1. Okay, so point number 1, x1, is just, if this is my vector 1, v, I don't put the arrow on top of it anymore because v stands for vector or velocity. Okay, so then I just say x1 equals, this distance corresponds to some delta time, delta t, dt. So it is the original position x0 plus delta time times the velocity at the original point, velocity 0. Okay. Okay. In general, it is the next point, xi plus 1, is always the current point, xi, plus some time step, delta t, time step, times the velocity at the current point. Is this a good method or not? Why is it not so good? Yes. If the flow is constant, and if the entire flow was going in the same direction, staying on the line, then if I were to follow an arrow, I stay on a line. I don't do an error. But if my flow is curved like this, then I compute this point, but the actual point on the curve is there. So there is an error here, right? It's bad. But how can you reduce the error? Huh? Cut it in half. Is that good enough? Maybe, maybe not. If cutting in half isn't good enough, you go to delta t over 4, delta t over 8. When is it good enough? Problems. We have problems, okay? Problems is the error control, okay? That's all I want to say, error control. Okay, here is the error. Now, what is the real problem that we actually have to solve? The real problem is an integral problem. It's an integral equation. And I just give you the mathematical formulation of the problem. And you see what it is that we really have to solve. And then I give you other methods to do it. One really has to solve. Really must solve the following. Okay. This is a highly curved streamline. This is the exact streamline, which I want to compute, but can never compute exactly in all cases, except in exceptional cases. Exact streamline. And we want to get, ideally for visualization, we would like to get, this is a curve. In the idealized world, we would like to get a bunch of points that lie exactly on the streamline, and then we would render that by having little segments connecting those exact points, right? There's a second degree of error coming in there because the curve is really curved. It's not straight lines. There's another problem. But that's not the point. The issue is at least the points we want to deal with should be points lying on that curve. So we have a first point or an intermediate point. We call it point I. And we want to get the next point, xi plus 1. This is the velocity here, right? The tangent. If I were to compute the next point on this, well, very quickly I would deviate a lot from that curve. It's ugly. Can't do that. So therefore, I have to use very small time steps. So what do I really have to solve is my next point, xi plus 1, is my current point. I want to get this guy, right? It's exactly on the curve. How can I force it to be exact? This is the next point I want. Xi plus 1 is the current point, xi, plus a vector, right? And the vector is this guy. This is the vector I want. Next point is previous point plus this vector. The issue is, how do I get this vector? A vector can be broken down into a sum of vectors, into a sum of differentially small vectors, little baby vectors. Where do I put those? They are living here. And I make them infinitesimally small and then sum them up. Summing in a limit sense is computing integral, right? And I integrate something over time, capital T for time, from ti to ti plus 1. And what do I have to integrate? I have to integrate little vectors along the curve, velocities at locations x, which depend on time, times differentially small times. This is a vector, right? A next point has to be a current point plus a vector, the difference vector. It's this vector. How can you think of that vector? Well, by adding all these little vectors, right? All these little vectors, right? When you add all these little vectors together, of course, they give you that vector. That's what that means. Huh? I'm just computing these short vectors, and I sum them up. But when I'm summing them and I go to ultimately length 0, then it becomes the integral, okay? Huh? So this is the sum of all the vectors along the curve. I sum them up. Huh? And it's velocity times time gives you a delta x, gives you a difference vector, right? Huh? Velocity is delta x over delta time, right? V equals delta x over delta time. So delta x is v times delta t, right? That's what this says. It's v times delta t, and I sum it up. along the curve. This is this difference vector, D, this guy. And this is this difference vector. That's what I have to do. In the limit, I have to go to infinitesimally small delta t's. So I cannot do that because it would take infinite time to do that, right? So I start with an initial time step, delta t, then if that's not good enough, I go to delta t over 2. If that's not good enough, I go to delta t over quarter. So I have to have an oracle that tells me when delta t is good enough. Okay, that's the next thing. So and now I just give you some methods how to do this. Two concrete methods, okay? Two methods. One, 0 was pretty bad. 0 is the Euler method. The other guy who was quite famous in this field is Hoyne method. Okay, this is a trick. You have a point, you call that point xi. You have a velocity at this point, you call that velocity I. And then you want to get the next location. And the method does it as follows. The method first walks to this point, and it's a helper point, and I call this helper point y. And this would be based on some delta t. So the helper point y is xi plus delta t times the velocity at point I. Okay. I can sample my vector field also there, so I can evaluate what the vector there is. This guy is the velocity at location y. I assume that I can compute that because I have vectors given all over the place, so I can use my approximation method to get a vector there. And so then I compute this midpoint. This guy is the midpoint between xi and y. So if it's the midpoint, m, then the midpoint m is just xi plus delta t over 2, midpoint, divided by 2, times the velocity. And now I want actually to get the next point, xi plus 1. And xi plus 1 is defined by starting at this midpoint and marching in the direction of the velocity up there. Okay? So now I march in this direction for some time. These are the same. Okay, this vector is that vector. So, and this is my xi plus 1. And xi plus 1 is my midpoint, m, plus the velocity. The velocity I computed at my helper point, namely y. Okay? Okay, that's the way it's done. Why is it done that way? It's in the math books. For certain for certain classes of vector fields that are of a certain class of polynomial behavior, we can show that these schemes are able to reproduce points on the streamlines exactly. That's where these methods come from. Okay? But again, they are only exact for certain types of functions. The ones that you get from a computer simulation are never exactly falling in that category. So there's always error. So that is one method. The other method that you should know, the other method is called a midpoint method. Midpoint method. How does the midpoint method work? Okay, you have your previous point, xi. The midpoint would be this guy. I call this midpoint now point y, helper point. So I have a velocity here. And going in this direction would correspond to half the time step. This would correspond to delta t over 2. This is my velocity at I. My helper point, y, would be given as current point plus half time step, delta t over 2, times the velocity at the current point, vi. Now I evaluate my velocity at this point, which I can do. So here I will have a certain velocity vector, this guy. So this guy is the velocity at y. And then I will use this velocity to apply it here and march in the direction for all of delta t. So these two vectors are the same, and I march in this direction for the entire time step duration of delta t, and get this point. Okay, xi plus 1 equals previous point xi plus entire time delta t times the velocity at the helper point y. Velocity at point y. Which method is better? Shoot.
So for the last one, the xi plus 1 is n plus 3y times delta.
You can plug it all in, right? For this guy?
No, the last one.
This one?
Yeah, it's we multiply by delta t over 2 then.
Plug. Here's the definition of m, put it in there. Right, here's the definition of vy, plug it in, you get just one closed form expression for the whole thing.
Well, I mean, I get it conceptually, but the definition.
Oh, yeah, you're absolutely right. I forgot something. You walk by half the time step, plus delta t over 2. Huh? Okay. So this corresponds again, delta t over 2. I should put that there. And m, going from here to here, corresponds to delta t over 2. This corresponded to delta t over 2, and this corresponded to delta t. So it's good to have this picture with these time durations in there, and it's always next point. A point is previous point plus some delta times velocity somewhere. Okay. It's correct now? Correct now, okay. Good. What is the most important method that you need to implement? Ideally, you should also understand where it comes from. Someone tells, jump here, okay, when you know what I'm writing down. What is this? Tell me. The Runge-Kutta method of order 4 works pretty darn well for most applications. So the Runge-Kutta method of order 4, just grab it from the web. You will find many implementations of it. And it's also a method like this, but it uses many, many more helper points and many, many more intermediate velocities and combines them in some magic way. Okay? You can assume that there are many other ways to combine multiple helper points with velocities, how it changes, and giving them certain weights. Okay? You can build these schemes for higher and higher order polynomial vector fields, to be precise. And so Runge-Kutta order 4 is one of those standard methods, just like a cubic spline is. Okay? It's related to cubic splines, actually. So take a look it up, and just grab an implementation that you can use, that you can rely on as being robust and correct. Okay, there are many implementations out there on the web of that method which are incorrect or not efficient. Use a good one. Okay. All right. So, yes.
How do they quantify the error for these methods?
How do they quantify the error for these methods? You mean how did they come up with these methods to begin with, or how you compute the error?
How you would compute the error?
You can compute the error in the following way. Okay. Now, since we are going into the error computation, we also have to go into what is called adaptive time stepping. Okay. Okay, let's do it. Adaptive time steps, or time stepping. Okay. First observation, this is the observation. If the given field is constant, if given field, vector field that is, if given vector field FLD is constant, then Euler, the simplest of schemes, the Euler scheme suffices. Euler scheme suffices. Okay. Otherwise, nothing suffices. Okay, what is a constant vector field? A constant vector field is a field where all the vectors are pointing in the same direction. This is a vector field where this arrow is always 1, 1, regardless where I am. Okay? That means that all the streamlines that I can possibly draw for this vector field look like this. This is the family, or this is the entire set of streamlines. Right? All the streamlines are lines. Therefore, when I pick this point as being my first point, and the vector there is this, I can use any arbitrary large delta t, no? Because I will always stay on that line. I can go here. This can make you go by huge delta t, right? Can do that. No error. Now comes the issue of error. The real world will always give me an error. How to handle error? First you have to estimate it. Is there error? How large is it? And if it's larger than some threshold, how to reduce it, right? So how to handle error? How do you do that? First, you need an effective means to determine that using different delta t's gives you different results, right? Okay. All right. This is the sequence of thinking, and I hope you get it. First, I compute a next point using any of these methods using some delta t. 1 second. Think of delta t as 1 second. Okay. I always try to compute the next point using a delta time of 1 second. Okay. Determine. The next point is always xi plus 1 using some delta t value. Okay, and you get an xi plus 1. Step 2, now you do the test. Is my field really a constant field or not? So now you go from delta t down to delta t over 2, and you try to get the same point by doing 2 steps, each one worth delta t over 2. Again, this is a trick. This is my current point, and I use a big delta t initially to jump there. Okay, this is xi, and I get my xi plus 1. Okay, and this corresponds to a huge delta t time step. Okay, now I ask, would I get the same point if I were to use 2 times delta t over 2? So now I compute a first point, this guy, a helper point, and this would correspond to a delta time over 2. And then I start here to again go by delta t over 2. And then by doing 2 hops, do I get to end up at the same point that I ended up with by doing just 1 big hop in the first place? You see that? If yes, then delta t is good. If there is a big difference between these 2 endpoints, then I should reduce my delta t. Okay? 2 is determine a point y using delta t over 2. Okay. Once you have that, then you start from y using the velocity at y to move forward for another delta t over 2. And you end up with a point which I call xi plus 1 tilde. Okay? And now you have to compare these 2 results. Is xi plus 1 the same as xi plus 1 tilde, or are they very little away from each other? Is there a small distance? You can also make a picture of that.
answer?
Uh-huh.
Doesn't that get computationally expensive?
No. Well, this is the price you have to pay. Okay. And the step 3 is, if these really differ, and the way you say that is if xi plus 1, the difference between them, x plus 1 tilde, is greater than some kind of threshold, what is the threshold, epsilon, then set delta t to delta t over 2, and you repeat the whole process, right? So the illustration, what does this mean, what I'm just talking about there? Illustration is, okay, I have my xi, and I want the next xi plus 1. I have a vector here, vi, and I compute my next point based on just Euler, the most trivial scheme there is. So the next point is obtained along this line here. This would be my initial xi plus 1, which is just xi plus delta t times velocity I. Okay, so this corresponds to delta t. And now I want to do 2 hops to get to my next point. Now I just use delta t over 2 as a time step, delta t over 2 in this direction, so I end up here. Okay. And now you get this m point. M is xi plus delta t over 2 times the velocity at the beginning. And now I measure, or I approximate, the velocity there. And there will be a different velocity if it's a non-constant field, right? If it was a constant field, it would still go in the same direction, but in general it's not. So here is the velocity at this m point, the midpoint. And now I march for delta t over 2 in that direction. Okay? So again, this corresponds to delta t over 2. I march there, and I end up at that point. And this point is I plus 1 tilde, the way I've called it before, which is my m point plus delta t over 2 times the velocity at this m point, at the midpoint. And in the ideal world, these 2 points would be the same, then there is no error. Unfortunately, the way I've drawn it, because the vector field changes, there is an error. So here is the error. This is the error. So the error is this difference, the length of this difference vector, xi plus 1 minus xi plus 1 tilde. And now you have to, well, the loop now goes as follows. If this error is smaller than my allowed threshold, then I'm happy with this point, I accept it. If this distance between these 2 points is too large, then I do not accept this guy. I will go back to the beginning, and I will reset my delta time to delta t over 2 and do the whole game again. Okay? So what does this mean? The implications. Adaptively computed streamlines. Computed, well, they are really streamline polygons. Okay? Streamlines, well, streamlines, synonymous. Streamlines. So if you have a flow field that looks like this, okay, and you use adaptive time stepping, then you will have a big spacing between the points that lie on the nearly linear stretches of the streamline, but then the spacing will shrink more and more when the streamline becomes more and more curved and the error grows tremendously. When you use a adaptive scheme, you have a non-uniform sampling. This is what you need, what you want, right? So you have a very big delta t to always begin with, and in many areas of linear behavior, this delta t is good enough, but then when the field starts to curve, then you need to switch to smaller and smaller delta t's, so you capture the curvature ultimately, infinitely. All right. That's it. And I'll see you Thursday. Boy, who has the diamonds? Someone has my diamonds.